So we're making progress, and we now know how to analyze the trade-off between potential energy and kinetic energy. And so let's apply it to a ball rolling along a surface. And the surface is going to accept the ball rolling in from the left, and that ball is going to roll up a hill to the top. And we're going to determine whether it can get over the top by calculating the relationship between kinetic and potential energy. And this is an interesting problem from the point of view of the physical processes going on, but we'll see it has a direct connection to a chemical reaction, because chemical reactions share the same kind of shape. That is, when two molecules collide, the electrons in the outer shell repel one another and create a repulsive barrier. And if those molecules are colliding at a velocity insufficient to mount the barrier, a chemical reaction will not take place. So let's work out the mechanical analog first, because we're already acquainted with the fact that we can calculate the change in mechanical energy as the final mechanical energy minus the initial energy. And because we're conserving the sum of kinetic and potential energy, we set that equal to 0. So let's borrow from our trajectory before, and let's write that the final energy is equal to the potential energy of that body when it reaches height h2. And that height h2 is the height of the barrier over which this rolling ball has to traverse before it can pass into the right-hand side of our diagram. Well, the initial energy is all kinetic energy, and it's the initial kinetic energy at position 1. So let's write this as 1/2 mv initials squared. But we know we can equate those two because of the conservation of energy. So we have that 1/2 mv initial squared is equal to mgh2 if and only if the ball has sufficient energy to reach that barrier height. So now we can set up criteria. Let's first set up the criteria that we just reached the top of the barrier. Now in that case, 1/2 mv initial squared has to equal exactly mgh2. But I can cancel the mass out of both sides, and that helps immensely because now I can calculate the required initial velocity. That's equal to the square root of 2 times the acceleration of gravity times the required height that I have to reach. If v initial is insufficient to reach the barrier height, then I know immediately that my initial velocity has to be less than the square root of 2 times the acceleration of gravity times the height. And if that happens, the ball doesn't reach the top. It stops somewhere between its initial position and the top of the barrier, and it comes right back down and exits at exactly the same velocity that entered. Now, if v initial is sufficient to pass over the barrier, then I know that my initial velocity is greater than the square root of 2 times the acceleration of gravity times the height of that barrier. And in that case, the ball will roll over the top of the barrier and descend down into the right-hand side of the diagram. And when it does that, it releases the potential energy of height and whatever kinetic energy it had, so that if the ball exits out of position 3, that's going to be equal to not only potential energy from the sum of height h2 and h3, but also whatever kinetic energy it had when it passed over the barrier.